Madam, maybe we can start. People are joining, but we can start with the introduction slowly.
Yes. Just a second, Kiran, just a second. We will
Yes,
start.
yes, sure. Yeah, sure.
Some reason my volume is a bit low.
So you might already know Devraj. Devraj, you meet.
Sorry, I was disconnected for a moment. I have a low bandwidth here. Kiran, shall I start then?
Yes, you can start. Yes.
So, good evening, one and all. I am Dr. Neeta Srivastav, Physics Department, Head of the Department of Physics, RJ College. And we are going to hear a very interesting talk from Dr. Nissim Kanekar. And it is regarding to physical constant. And there are many questions which are always, pondering our mind regarding physical constants. And as we know that some of them are constants are really constants, but some change with time, and values are different at different places. So maybe we are going to know something new about it, that how it changes, how these constants changes with time. We are having here Dr. Nissim Kanekar, and let me just give you his brief introduction. He did his BSc Physics from University of Pune, and MSc from University of Pune itself in 1995. Then he did his PhD doctorate from University of Pune itself. Then he joined Max Planck Fellowship for his postdoc, National Radio Astronomy Observatory, USA. And he has been awarded many awards. Some of them I will just read over here. It's a long list of his awards. So Jansky Fellowship from 2004 to 2008, National Radio Astronomy Observatory, USA. NOVA Fellowship from 2002 to 2004, Captain Institute, University of Groningen, the Netherlands. And there are many other fellowships and awards in his name. Few of them are Shanti Swarup Bhatnagar Award for the Physical Sciences, 2017, and Hariom Prerit Vikram Sarabhai Award for Space Sciences, 2015, and GST Swaranjan Jayanti Fellowship 2015, Delta Lectureship Award in 2014, and again, I would repeat here that Max Planck Fellowship, National Radio Astronomy Observatory, USA, and ESO Visiting Fellowship, that is in 2005, European Southern Observatory, Chile. So, sir, without wasting much of your time, we would like to hear from you. So, over to you, sir.
Great. Thank you, Dr. Srivastava. And thank you, Kiran, for the very kind, invitation.
Yeah.
It's a pleasure to give this talk.
It is
Although, of
our
course,
pleasure too. I would just, how would you like to take the questions?
anytime you
Should we
like. Yeah.
ask-
So if somebody has
They can
questions,
put in
during,
chat. Yeah.
yeah, if somebody has questions in the talk, just stop me and be happy to answer them then, or to at least address them then. And otherwise, at the end of the talk,
Yeah.
whatever.
They can
I mean,
put it
it's
in the
completely
chat
fine.
box and we will read it out. Yeah. Okay.
Yeah.
Yes.
So thanks, Kiran, for the invitation. And it would have been nice to have been, present, with you. But I guess that's the best we can do these days. So I'm going to be telling you about how we use astronomical spectroscopy to probe changes in the fundamental constants of physics, to test for changes in the fundamental constants. And one of the telescopes that we use for these studies is the one shown down here in the background image, the giant meter wave radio telescope. This is a picture taken by Prem Kumar from the Narayangarh hill above the GMRT. And you can see about 17 or so antennas which make up the GMRT. The GMRT is made up of 30 antennas spread out over about 25-kilometer diameter. And I would urge all of you to come over and have a look at the telescope. There are a few things more lovely than a functioning telescope. It's one of the reasons that I got hugely excited about observational astronomy about 25 years ago. So I would urge you to come and take a look, organize a college visit or something to the GMRT. We do host colleges quite happily. Okay, so this is the broad outline of the talk. I will first try to convince you that we should care about the possibility of fundamental constant evolution. And a very short way of addressing this question, as with most questions in physics, is via a quote by Feynman. And so, Feynman, who was famous for these short, pithy quotes, said about the fine structure constant alpha that its value is one of the greatest damn mysteries of physics. And Feynman was known for these, fairly sharp lines, shall we say? And but one of his competitors for the title of the top physicist of the second half of the 20th century was Julian Schwinger. And Schwinger was not known for being as fluent with language as say Feynman was. Certainly not as sharp with language as Feynman was. But the importance of alpha was as clear to Schwinger as to Feynman. And so to illustrate this, I've shown the car over here on the bottom right, and that's a Flavia Lancia 962 model. It was Julian Schwinger's car when he was at Harvard in the early 60s. It was a powder blue car, a powder blue Flavia Lancia, and which I have taken the liberty of redshifting in keeping with this talk. But the important thing is the license plate. The license plate is 137039, which is, of course, the value of the fine structure constant, the inverse of the value of the fine structure constant, 1 upon 137039. And so, the fine structure constant value is sufficiently important to Schwinger that he felt that it merited a place on his license, so to speak. And that kind of tells you how important the fine structure constant is and why we care so much about it. But of course, I'll give you a little bit more detail about it. Oh, I should mention one thing, which I always mention at the start of a talk. In case I'm speaking too fast, I'm completely used to being stopped and told to speak slowly. Please do so. Please feel free to stop me whenever you like. And of course, please feel free to ask questions during the talk. So after motivating studies of fundamental constant evolution, I'll give you a little bit of a background on spectral lines. And we'll try to convince you that you should also love spectral lines and do spectroscopy for the rest of your lives. I'll try to illustrate the basic issues in probing changes in the fundamental constant using lab measurements, basically using atomic clocks. And so I'll tell you a little bit about atomic clocks and how people use atomic clocks to probe changes in the fundamental constants. And then I'll segue into cosmology, give you a little bit of background about cosmology, just a little bit, just to get you up to speed with terminology, especially redshifts. I'll move from there to redshifted spectral lines and how we use redshifted spectral lines to probe changes in the fundamental constant, specifically the fine structure constant and the ratio of proton mass to the electron mass. I'll do a very brief thing on radio spectroscopic studies and tell you why you should like radio astronomy much more than any other branch of astronomy. I'll tell you where we are today and where we hope to go over the next decade or so. So that's the broad plan at the top. But before we start, why do we care? So again, to answer the question of why do we care, I have to first tell you what are fundamental constants. So fundamental constants are essentially free parameters of a theory. They're quantities that are not predicted by the theory, whose values are not predicted by the theory, but which are free parameters. They are parameters in the equations of a theory, which are not predicted, and so which have to be measured by experiment and then put in my hand. And these include quantities, for example, the speed of light, the electron charge, the Planck constant. And the two quantities which are important for the rest of this talk, the fine structure constant, alpha, which is E squared upon H bar C, 1 upon 137 approximately, and the ratio of the proton mass to the electron mass, which I will denote as mu from now on. So alpha and mu will be the two heroes or heroines of this talk from now on. And you will notice that there are 3 of those quantities are in blue and 2 are in magenta. I'll tell you why in a minute. But the important point to take home from this is, one, that these are free parameters, but 2, that the free parameters of a theory will depend on the theory. So for example, the parameters of classical electromagnetism, for example, the fine structure constant, will not necessarily be the same as the free parameters of a more general theory, like say the standard model of particle physics. So the standard model of particle physics has a bunch of free parameters, but alpha will not be one of them. There will be higher order parameters in a more general theory. So therefore, but within each of these theories, these quantities are not expected to change with space or time. These quantities are expected to be fixed within the confines of this theory. And if you like, they tell you a little bit about our ignorance about the universe. Because if there are a set of free parameters that, whose values we don't understand, that basically tells you what the theory is not telling you about with regard to the universe. And so our current, favorite theories, our current best physical models of the universe are the standard model of particle physics and general relativity. And there are today 22 free parameters in the standard model and general relativity. And you can add another 3 or 4 if you want to account for neutrino masses. So about 22 free parameters, maybe 26 if you put in neutrino masses. And this tells us our level of ignorance about the universe today. And quite possibly, those parameters will turn out to be not free once we come up with the unification theory, which combines the standard model and relativity. So now, why do we care about fundamental constant evolution? A pragmatic view, a fairly, down-to-earth, grounded view, is that these are assumptions of the standard model and relativity. The constancy of these 22 parameters are basic assumptions of the standard model and relativity. And so by testing whether these parameters are constant, you are basically testing the assumptions of the standard model and relativity. And if you find that these parameters are not constant, you will have demonstrated immediately that the standard model is wrong. So this is an important way of probing your current best theoretical models. It's by testing their assumptions. And the fundamental constant evolution tests are similar to tests of, for example, local position invariance, Lorentz invariance, violation of the equivalence principles. All of these are assumptions that go into our current models of the universe. And so testing these is important in order to work out whether our current model, our best current model, is actually a good model. And so far, the standard model relativity have passed all these tests so far. So that's a pragmatic view of probing fundamental constant evolution. A more philosophical view, and perhaps a more deep view, is that changes in these low energy coupling constants, quantities like alpha, the fine structure constant, which is the coupling constant of electromagnetism, are actually expected in higher dimensional unification theories. So these higher dimensional unification theories are basically models that try to combine or unify the standard model of particle physics and relativity. And it's been shown that you cannot do this in 4 dimensions. You need typically about 10 dimensions to do this in. And it turns out that these low energy coupling constants are expected to change in these higher dimensional unification theories. Expected is in quotes because it's not a prediction. It's an expectation. So far, every single unification theory that has been looked at suggests or indicates that these constants should change with time. And so it's kind of a generic prediction of these higher dimensional unification theories. And it comes about for fairly, simple, from a very simple argument. The argument is simply that when you have these extra, let's say, when you have 10-dimensional theories, this begs the question, where are these extra dimensions? And the extra dimensions are spatial dimensions. So now if you think about the 4 dimensions of relativity, you have 1 time dimension and 3 space dimensions. Now, if you take a step back and think about Euclidean geometry, then your 3 space dimensions basically go from -infinity to +infinity. Straight lines, if you like. Let's think of flat space for a minute. And so you just have a straight line. Now, if I have a dimension going from -infinity to +infinity, I have no length scale in the problem. So I have to first, if I want to tell you my height, for example, I have to first define that the length of, for example, a meter or a foot or an inch or some unit of length. And then I will tell you my height in units of that length. But I don't have a natural length which relative to which I can tell you my height or any length in the universe. And so I have to define the length in normal Euclidean, in a Euclidean metric. However, in these higher dimensions, the way in which you hide these dimensions is interesting. The way you hide these dimensions is that you do a process called compactification. And what you basically do is that you wrap these dimensions on themselves. These dimensions are not straight lines, they're circles. So they're wrapped around themselves as circles. And the size of these circles is very small. It's at the quantum scale. And the argument is that these are sufficiently small that you can't observe them. And that's why you can hide them. But now you have a problem. The problem is that the moment you've wrapped the dimensions on a circle has a well-defined length scale, the diameter of the circle. So now these dimensions, unlike the normal Euclidean dimensions, actually have a length attached to them. So now this is interesting because now this gives you a difference between these extra dimensions and the normal dimensions. Why does this matter? This matters because it turns out that the low energy coupling constants, and this is the generic prediction of unification theories, they are functions of the size of these dimensions, of the scale length and the diameters of these dimensions. Why does this matter? This matters for a funny reason. It matters because the universe is expanding. And we'll talk about that a little bit later in this talk. But the universe is expanding. And as the universe expands, the normal 3 space dimensions stretch. But as the 3 space dimensions stretch, even these extra higher dimensions stretch. And when the higher dimensions stretch, what happens is that their scale lengths, the diameters, increase in size. And when the diameters increase in size, because the coupling constants are functions of the scale lengths of these higher dimensions, the coupling constants change. And this is the reason that this prediction or expectation that the low energy coupling constants must change once you have a higher dimensional unification theory is a completely generic prediction. And that's beautiful because every single theory predicts this, but there's a catch. The catch is that we don't know what the time scale of these changes is. Since every theory predicts it, different theories predict different time scales. So if you want to measure, if you want to probe these unification models, you must probe timescales from of the order of a few seconds, a few minutes, a day, all the way up to the age of the universe, about 13 billion years. And that's a problem. So you need to come up with experiments or observations that can probe a wide range of timescales. And that's what I'll tell you about in this talk. But the beauty of this prediction is that unification of the standard model and relativity is one of the big open questions in physics today. And the problem with unification is that unification happens at very high energies of the order of 10 to the 19 giga electron volts. And these are energies which we are not going to reach in the foreseeable future, even if you're a crazy optimist. And so how do you probe unification? What you need is low energy probes of unification theories, energies that we can actually reach in the lab or in the universe, but we still have predictions from the unification theories at these low energies. And fundamental constant evolution is an example of such a probe. It's a prediction of unification theories that we can actually hope to observe at our energy scales. And that's why people are so excited about it. So that's the reason why people care a lot about changes in the fundamental constants. One is just testing the models, the best model that we have. But two, and perhaps more important, is that it provides us a window onto these very high energy theories, which we hope will let us take the next step in understanding the theories that describe the universe. So now, which constants do we look at? Which constants do we probe in their changes? And the standard constant that everybody looks at is the fine structure constant, alpha, which is the coupling constant of electromagnetism. And the reason we look at alpha is simply that alpha sits in all, the easiest things to observe are electromagnetic effects, radiation, for example. And alpha sits in all of those equations. So therefore, alpha changes in alpha are what we observe, or what we try to observe as much as possible. But interestingly, fractional changes in the proton-electron mass ratio, the quantity mu over here, are expected to be of the order of 100 times higher than an alpha, depending on the theory, 10 to 500 times higher than an alpha. So therefore, it may actually be easier to detect changes in the proton-electron mass ratio rather than alpha. And so mu is another quantity that people try to observe, try to test for changes in, both in the lab and at cosmological distances. But the question, which kind of jumps up is, how do you test for these changes? First of all, what are the constants you look at besides, alpha and mu? And secondly, how do you do it? So the basic technique boils down to, first of all, you should test for changes in dimension-less constants. And so if you go back to the previous slide and you look at the first line or the second line, you see there are three constants over here, C, E, and H bar, which are dimension-full constants. And then you have two constants over here, alpha and mu, which are dimensionless. Alpha is 1/137, and mu is a ratio of two masses, so it's dimensionless. The point I want to make is that you should test for changes in quantities like this, in coupling constants or the ratios of particle masses. And the reason for that is that the quantities C, E, and H bar have dimensions. The dimensions are meters, seconds, kilograms, whatever. And the problem is that if you try to test for changes in dimension-full quantities, like the speed of light, you get into confusion with units. Because the definition of a unit often implicitly assumes that some parameters don't change. So for example, the definition of a meter is based on the fact that the speed of light is constant in a vacuum. It's defined as the distance traveled by light in 1/299,792,458 seconds. And so that assumes implicitly that the speed of light is constant. And so now if you try to use a quantity which has dimensions of a meter, if you try to probe changes in that quantity, you have already assumed that the speed of light is constant at the start of in your definition itself. So you get into trouble. It's like a dog chasing his own tail. And so therefore, you can bypass all these issues by testing for changes in dimension-less constants. So for example, alpha, and that's the reason that many of us will focus entirely on alpha, things like alpha, mu, and so on. So therefore, that's what we should be looking at, alpha and mu. That's what I'll be looking at for the rest of this talk. How do you go about this? Again, the approach is fairly simple. What you do is that you measure the same quantity, the same measurable or the same observable, and this could be time, redshift, some quantity which you want to measure, with two different methods. And the idea is that the two different methods should have different dependencies on some constant, for example, alpha. And then the idea is that if the constant changes, the two techniques or methods would give you different values for the measured quantity. And so this is slightly subtle. Remember, you're not actually now, by this approach, you are not actually measuring a value of alpha. What you're doing is measuring some quantity, which could be time or redshift. And the measurement process depends on alpha. Now, if alpha changes, the measurement process will give you a different result for the measured quantity than you would have gotten if alpha had not changed. But how do you know that alpha has not changed? Or how do you know what the value of alpha is? And that's why you want a second method. So you want two methods which have different dependencies on some constant to measure the same quantity. And the idea is that the value of that quantity has some absolute value. So now I can simply measure that quantity. If I get the same answer, it means that alpha has not changed. If I get different answers, it means that alpha has probably changed. And that's the game over here. The techniques that you come up with are all based on the same philosophy that you want to use two different methods with different dependencies on a single constant. So how do you do this now in more detail? All of the techniques that we use to probe changes in alpha, mu, and so on are based right at the bottom on quantities called spectral lines. And so let's take a brief digression onto spectral lines. So spectral lines are basically quantum mechanical transitions in atoms or molecules between two energy levels. So they're simply, you have let's say an electron, or more generally, you have a species which has two energy levels, and the species can make a transition from one energy level to the other with the emission of a photon. And that photon has a precise energy and hence a precise frequency. And so these are inherently narrowband phenomena. They come out at a very specific frequency. And so this plot over here on the top right shows the Bohr atom with basically, the n equal to 1, n equal to 2, n equal to 3, a hydrogenic atom with an atomic mass number of Z. And it's got whatever Z electrons divided amongst these various orbitals. And what happens over here, if you think of the hydrogen atom, the Z is 1, then a transition to n equal to 3, the principal quantum number 3 to n equal to 2 comes with the emission of a photon. And this transition gives you what is called the Balmer alpha line. So all transitions to n equal to 2 give you the Balmer series of hydrogen, which is a well-known series in the late 19th century. In fact, that is what Bohr actually used in the Bohr model. He predicted the wavelengths of the Balmer series. And so this is an example of a quantum mechanical transition. And these lines could be an emission or an absorption. So in this particular case, we are jumping from a higher energy state to a lower energy state. That produces emission. You emit a photon. On the other hand, suppose you have a background source, like a star or a quasar, then you could have a particle, you could have an electron in this state, n equal to 2, and the atom absorbs a photon, and that causes the electron to jump to the higher energy state. So to illustrate this, you can look at the spectrum over here, which is for, let's say, a black body, white light spectrum, which is in the optical. So this here the axis is wavelength in nanometers, and you go from about 3,000, roughly 750 to about 7,500 angstroms. So the 375 to 750 nanometers, going from all the way from violet to blue to green to yellow to red. And that's a continuous spectrum. So you have this smooth radiation at all of these wavelengths. But if you look at the hydrogen, suppose you had hydrogen gas and you heated the hydrogen gas, then the emission produced by this hydrogen gas would actually be a bright line, a bright spectral line at 6,563 angstroms over here, which is Balmer alpha. Another bright line at about 4,800 angstroms, or 486 nanometers, which is Balmer beta. Another one over here, which is Balmer gamma. Another one over here, which is Balmer delta, and then a lot of other much fainter lines. So that's the hydrogen emission spectrum. On the other hand, if you looked at, for example, the sun, or you looked at some hydrogen gas with a source behind it, then what would happen is that you'd see absorption at exactly the same wavelengths. So you'd see Balmer alpha and absorption, Balmer beta and absorption, and that's why this is black over here. So now you have some background source behind this gas, and now you see absorption, and that's pulling out photons, pulling out radiation at exactly this wavelength. So that's an absorption spectrum. This is an emission spectrum. And so that's the broad picture of spectral lines. And we, of course, observe all kinds of spectral lines in astronomy. And I'll show you some examples of them in a short while. The important thing, though, with spectral lines is that they come from a wide range of physics. So for example, the Bohr atom, in these transitions in the Bohr atom, the transitions are simple electronic transitions. They're transitions that go from a principal quantum number state to another principal quantum number state. On the other hand, you can also have electronic fine structure, which is, if you like, the Sommerfeld atom, or the Sommerfeld model of the atom. You can have hyperfine structure as you get more into more complicated quantum mechanics. You can have hyperfine structure, which is a dipole interaction, dipole interaction. You can have molecular rotation in molecules. So these are now simple atoms. Now, if you move to molecules, you can have the whole molecule rotating and giving you different energy states because of the rotation of the molecule. You can have what are called inversion transitions, where the entire atom or molecule basically gets inverted around. There's a mirror axis within the atom or molecule, and you can have an inversion across that axis. So there are all kinds of physics that govern these transitions. And the important thing is that because the physics is very different, it means that the transition frequencies have different dependencies on the fundamental constants. So for example, the transition frequency for this kind of a transition in the Bohr atom is not the same as the dependence of, for example, a fine structure transition or a hyperfine structure. And I'll show you what I mean in a second when we get into more details of atomic clocks. But for now, the point to be taken is that different types of physics give you different dependencies of the transition frequency of this frequency over here, the exact frequency or wavelength at which the transition happens upon the fundamental constants. So why does this matter? This matters because the line frequency actually identifies the line. The frequency for a specific line is absolute and known from the lab. Any shift in frequency, in the measured frequency, is because of motions. And this is basically the Doppler effect. And that's what you see over here, where if you have, for example, a star moving in an orbit, you see that as the star moves away, all these lines move in that direction. As it moves away now, as it moves away, you can see that all these lines are moving. As it comes towards us, these lines move towards the blue. Again, as it moves away, they move towards the red, and so on. So that's just a Doppler effect, that when you have an object moving away from you, its sound waves or light waves get redshifted. They're shifted towards the red part of the spectrum. The wavelength becomes longer. On the other hand, if the object is moving towards you, its waves get blue shifted. They're shifted towards shorter wavelengths. That's all there is to it. It turns out that this is extremely important in astronomy because you can actually determine an object's motions from the redshifts or blue shifts of its line. So for example, over here in this particular picture, I can tell you that the star is moving away from us or towards us. It's in an orbit just by seeing the fact that these redshifts and blue shifts are periodic. So I can immediately tell you that, hey, hang on a minute, the star is in an orbit with exactly this period. And frequently I can then work out the object around which it's orbiting, work out its mass and so on. So this kind of stuff is a critical ingredient in astronomy. And this is a basic Doppler effect. We'll worry about cosmological redshifts in a short while. But so having said this, you have a bunch of these spectral lines, narrowband phenomena. How does this matter for fundamental constant evolution? This matters, let's think about this in the point of view of atomic clocks. So in atomic clocks again are based on spectral lines. In an atomic clock, the time that you measure in the clock, it comes from the frequency of a particular spectral line between two energy levels in an atom. And the same thing is true for a molecular clock. So the way it works is that what you count is the number of times that this transition happens. So, and you define that a second is so many transitions of this particular frequency. So for example, in cesium, which is our favorite clock today, in fact, the second is defined from the cesium clock. The cesium 133 transition, which is at this frequency of 9.1926, whatever gigahertz in this clock. That's an example of a spectral line, which is the basis of a cesium atomic clock. The important thing is that, as I said earlier, all spectral line frequencies depend on alpha and or, for example, a mu. So in the case of the cesium line, the cesium 133 line, it's a hyperfine line. And it turns out the hyperfine frequency, you can show this theoretically, is proportional to alpha square and is proportional to 1 upon mu. So if I build a cesium clock in the lab, then the frequency of the cesium of the line inside the cesium clock will depend on alpha square and it will be inversely proportional to mu. On the other hand, suppose I build an aluminium clock, an aluminium plus an ionized aluminium clock. An aluminium plus clock is based on principal quantum number transitions, resonance transitions as they are called. And it turns out that for such a clock, for such a spectral line, the frequency to first order does not depend on alpha. So the frequency basically is constant. It does not depend on alpha to first order. So now consider that you build these two clocks and you place them together next to each other in the lab. One cesium clock, one aluminium clock. And let us say that alpha changes. So if alpha changes, of course, because the cesium frequency depends on alpha square, what will happen is that the cesium frequency will change. But remember, the aluminium frequency does not depend on alpha, so the aluminium frequency will not change. So now you have a clock where the cesium frequency has changed and the aluminium frequency has not. But remember, the clock speed, the time on the clock, depends on the frequency of the transition. So because the cesium frequency changes, the cesium clock speed would change and the aluminum clock speed would not change. And so as a result, if you just simply sit and watch these clocks for a year or 2 years or 5 years, the clocks will show different times later. And that's the measurement. That's all you have to do. You have to build these clocks as accurately as you can, place them inside a lab, seal that lab, prevent external effects from affecting the clocks, and simply watch the clocks. Measure the time on the clocks for as long as you can. Very simple measurement. Of course, very hard because you have to build the clocks really well. You have to shield the clocks really well. But philosophically, very simple. All you have to do is to compare the times on two different clocks for a few years. And this has given us what is, even today, the best result on changes in the fine structure constant on timescales of about a year. And so about roughly 13 years ago, Rosenband et al. Found that 1 upon delta time, delta alpha by alpha. So this quantity delta alpha by alpha is basically the fractional change in alpha. So delta alpha is basically alpha minus alpha naught divided by alpha naught. So that's a fractional change in alpha divided by time over here, which for them was 1 year. So this quantity is basically 1. So delta alpha by alpha over 1 year was less than 4 times 10 to the minus 17. So alpha changes by less than 1 part in 10 to the 16 over a period of 1 year. So that you might say is a spectacular result. It's just amazing, right? That you can actually measure something so accurately. And that's what they published about 12 years ago. And remarkably, this is still the best result today after 13 years, after more than a decade. It turns out that what we are limited on today is things like the Earth's gravitational field not being exactly the same. If I place 2 clocks at different locations, the Earth's gravitational field is not the same at this location and this location. And since the time of the clock depends on gravity, it turns out that these differences in the Earth's gravitational field matter. And so the next step now is to actually put these clocks on the International Space Station and try to compare them over there. And that's a plan people have had for a long time. And the hope is that we can improve things by about maybe 2 orders of magnitude via putting them on the space station. And people are talking about doing this. So atomic clocks are wonderful. They give you this spectacular sensitivity and they give you great control over systematic effects. And you will see in a minute that systematic effects are the biggest problem in these measurements. You really need to control, you're looking for really tiny signals and you need to control systematics as well as you can. And because these are lab measurements, they give you wonderful control on systematics. But the problem is that atomic clocks probe changes only on timescales of a few years. And these are tiny fractions of the age of the universe. And remember, I told you that we don't know the timescale on which the constants change. They could be timescales of a few years, in which case atomic clocks will catch them. But what if they change in timescales of billions of years? Or the timescale of the change of the age of the universe? You will not simply measure them if you were using only atomic clocks. And this brings you to the need for astrophysical or maybe geological techniques. And that's the basis of these astronomical probes of changing fundamental constants. So let's now do a brief digression to cosmology, so as to get a feeling for what kind of objects are we looking at when we try to probe changes in the constants using astronomy. Now, if you were telling somebody, your favorite friend, something about the universe, the thing that you should tell them, the thing that describes the universe most, best of all perhaps, is that all galaxies beyond some distance are moving away from us. The universe is expanding. And this was a shock for people about 100 years ago. In fact, it was almost exactly 100 years ago that Edwin Hubble and Milton Humason discovered that the universe was expanding. Until then, right through the history of the universe, people had no idea that this large-scale universe was moving apart. So the universe is expanding. And we know this to be definitely true today. And as I said earlier, a redshift happens when a wavelength of light shifts to a higher wavelength when you have a source that's moving away from you. And a higher velocity gives you a larger redshift. So that's just a normal Doppler shift. But now when you have an expanding universe in which galaxies are moving apart, you wind up with essentially cosmological redshifts, which are denoted by Z. And these are defined as lambda observed, the observed wavelength, is simply lambda rest, the rest wavelength, multiplied by 1 plus z. Very simple definition. In fact, that's the only, well, that's one of the two equations that I'm going to use in this talk. The second equation is on the next line. So that's just a simple down-to-earth equation describing the observed wavelength compared to the wavelength that was emitted by the galaxy, which you're observing, which you're looking at. And z is the redshift of the galaxy. So that's a cosmological redshift. And that's what we have to play with in our changes in fundamental constants. Now, Edwin Hubble also found an important relation between the velocity of a galaxy and its distance from us. And this has now been enshrined as Hubble's law. Essentially, V is equal to h naught d, where h naught is the Hubble's constant. And what this means is that more distant galaxies have higher redshifts. So the further away a galaxy is, the higher its redshift. And we know this to be correct even in today's universe, where we are actually measuring velocities which are measuring redshifts which correspond to velocities higher than the speed of light. So of course, that equation does not hold once you get to relativistic speeds. But for low velocities, that equation holds. But the broad result that more distant galaxies of higher redshifts is still true today. Now, suppose you have more distant galaxies of higher redshifts, then because the speed of light is finite, this immediately tells you that when you have a distant galaxy, you're seeing it as it was in the past. I mean, this is fairly simple. If you look at the sun, for example, the sun is about 8 light minutes away. So we are seeing the sun as it was about 8 minutes ago. And to give you a feeling for how this connects to redshift, since more distant galaxies have higher redshifts, an object at a higher redshift is seen as it was earlier in the universe than an object at the lower redshift. So for example, an object at a redshift of 0.1 is being seen as it was 1 billion years ago. So 1 giga year ago. An object at a redshift of 1 is being seen as it was about 8 billion years ago. An object at a redshift of 6 is seen as it was about 12.8 billion years ago. And the universe, in our current best cosmological model, is about 13.7 billion years old. So an object at a redshift of 6 is very close to, in terms of time, to the start of the universe. It's within a billion years of the start of the universe. An object at redshifts of 10 is about 13 point something billion years ago. And so this gives you a feeling. So now, if I can observe a galaxy at a redshift of 1 and measure fundamental constant evolution in that galaxy, I'm basically measuring evolution in the constants on timescales of 8 billion years. That's the game over here. So that immediately tells you that by observing these early galaxies, if you can find a way of probing changes in the constants, you're probing changes on timescales of billions of years. And that is the game. So how do you do this? The way you do this is by measuring the galaxy's redshift, again from its spectral lines. And this shows you an example of a nice plot from Joe Lisker's webpage, which gives you, it kind of is a nice plot because it shows you both emission lines and absorption lines. So let's say that you have a background quasar, which is like a torch, basically. It's a big active galactic nucleus in the center of a galaxy, pointing towards us. And we're observing this thing with our favorite telescope. And what you see is that you see the spectrum, which is plotted over here as a function of observed wavelength. And this is about 5,000 angstroms. It's in the optical. That's about 3,000, 4,000, 5,000, and 6,000. And you see this powerful emission line over here. So there's this continuous emission here. And with these, lots of these, what are called absorption lines. And then you see this continuous emission, this red curve over here, and a few narrow absorption lines over here. But this emission is sitting on top of this continuous emission. So that's like the continuous emission that we saw a little while ago. And then you have a spectral line over here, which it turns out is the Lyman alpha emission line of hydrogen. But we know that Lyman alpha is at a wavelength of 1215 angstroms. And we are observing this line at about 4,800 angstroms. So how is that possible? That's possible because this quasar is at a redshift of 3, which means that your observed wavelength is 1 plus z, which is 4, times 1215 angstroms, which gives you approximately 4,800 angstroms. So that's Lyman alpha. Then you have another funny bump over here, and that turns out to come from quadruply ionized nitrogen. So that's nitrogen emission. You see another bump over here in emission. That comes from triply ionized silicon. And we know all of these in the lab. You see another bump over here, that's triply ionized carbon. So these are all emission lines from this object. So that's the emission spectrum of this quasar. But now what about all these narrow lines? Where are these coming from? So first of all, let's look at the stuff which is at lower wavelengths than quasar Lyman alpha, where you see this kind of this patchwork of absorption lines, which are so tight that you can actually not even see this, this continuous emission over here. Almost all of it is absorbed. This absorption is coming from hydrogen in the intergalactic medium between us and the quasar. So this is just really faint intergalactic hydrogen clouds, and they produce Lyman alpha absorption of the at their rest Lyman alpha wavelength. And each of these small narrow lines is coming from a small, very wispy hydrogen cloud between us and the quasar. But then every so often, you see this powerful absorption that you see over here. And such an absorption line comes when you have a big galaxy between us and the quasar. So here you have this galaxy over here, which is at a lower redshift than the quasar, and that produces very strong Lyman alpha absorption. And the fact that you see this powerful absorption tells you there must be a galaxy over here. But what is even more interesting is that in addition to the hydrogen in this galaxy, the galaxy also has metals. It has iron, it has silicon, nickel, all kinds of metals. And those species actually produce absorption at longer wavelengths. So this, for example, is a singly ionized nickel line, a very weak line over here. This is a singly ionized silicon line over here. This is triply ionized carbon, 2 lines over here from carbon. This is an iron line, singly ionized iron. So all these narrow lines are coming from metals in this galaxy. And these correspond to the redshift of the galaxy. This is aluminium, doubly ionized aluminium, neutral magnesium, singly ionized silicon, doubly ionized aluminium. And we can actually observe all these lines in the lab, and we know exactly what the wavelengths are. So we can simply, by dividing by 1 plus z, we can work out we can identify all these lines. So these are the lines that you see in the universe. And the beauty is that galaxies have been detected today out to about redshifts of 10. So you see emission lines like this out to redshifts of 10, and you see absorption lines like this out to redshifts of about 6. So redshifts 10 is about 13 billion years ago. Redshift 6 is about 12.8 billion years ago. So by using these absorption lines, you can in principle probe changes in the constants all the way out to about 12, 13 billion years ago. And that's the game. So how do we do this? The way we do this, again, fairly simple. The line rest frequencies depend on alpha and mu. And of course, that dependence comes from line physics. And it's the same equation that we saw a little while ago, that if lambda observed is the observed wavelength, which we measure, and lambda rest is the lab wavelength, the same transitions wavelength in the lab, then this equation defines the redshift of the galaxy. But this equation, which seems very trivial, actually has a very fundamental assumption inside it. This basically assumes that the lab wavelength is the wavelength at which the emission happens at the galaxy redshift. It assumes that lambda rest does not depend on redshift. And that's a foundational assumption. So now suppose alpha were to change with time or were to change with redshift, then lambda rest would change with redshift. But you would not know this, right? How do you know that lambda rest has changed? So you will simply use the rest wavelength of the line from the lab in your equation. You will measure lambda observed, and you will determine the wrong redshift by using this equation. So you measure this, you use this quantity from the lab, and you infer the redshift z, and you infer the wrong redshift. And you won't even know about this because you don't know that how lambda rest has changed. But suppose you have a second line now. Suppose you have 2 lines to the same galaxy with different dependencies of lambda rest upon alpha. Then what will happen is that for each line, I will write this equation. For each line, I will use the wrong lambda rest in the equation. And for each line, I will determine a different redshift for the galaxy. And that's the game. That basically you're measuring the redshifts and you're comparing these 2 redshifts. If the redshifts agree with each other, then alpha is not changing with time or with redshift. If the redshifts are different, then that's telling that alpha is changing with time. And you can now use this technique to study changes all the way out to redshifts of 6, about 13 billion years or so ago. And so it's fantastic, right? You suddenly have a way of going from atomic clocks which are probing things at timescales of 1 year, all the way out to 13 billion years ago. And this is exactly what you wanted. You wanted to probe a whole range of timescales. The next question, which kind of immediately comes up, is should you use absorption or emission? And it turns out absorption lines are much better for this because they are narrow and they trace a really small beam through the gas. You're pointing at a really tiny background quasar. You pick up a really tiny amount of gas. And so it's simple. And so absorption lines tend to be better for probing changes in alpha and mu. So let's look at an illustration of how you do this. So what you do is that you measure an absorption line, right? And so what I've done is that in the left panel, I've plotted two cases. I've considered the singly ionized magnesium line at a rest wavelength 2796 angstroms from a galaxy at a redshift of 1. And there are two curves plotted over here, although you'll see visually only one. One of them has delta alpha by alpha of 0, and one of them has delta alpha by alpha of 10 to the minus 4. So alpha changes by 1 part in 10 to the 4, very small change. And the point is that for magnesium 2, I can show theoretically the lambda rest does not depend on alpha, the first order. It depends very weakly on alpha. And so even if alpha changes, it doesn't produce any difference in the observed line. So that means that I will not see a change in the redshift. The curve that I will get, the line that I will detect, will be the same no matter whether delta alpha by alpha is 0 or delta alpha by alpha is positive or negative. It won't affect the magnesium 2 line. But now look at the right panel. In the right panel, I'm plotting an ion line, singly ionized ion from the same galaxy, redshifts of 1. And now you'll see that the red curve is for delta alpha by alpha of 0. And that's clearly offset from the blue curve, which is delta alpha by alpha of 10 to the minus 4. And that's simply because in ion 2, lambda rest depends very strongly on alpha. And this means that if alpha changes, lambda rest changes, and I will immediately get a change in the redshift of the galaxy. And so that's what you're trying to do. You're taking two lines. You have a single measurement, which is the galaxy redshift. Technically, you're actually measuring the line wavelengths. What you're doing is that you're measuring the exact wavelength of this observed line over here. The two techniques are different spectral lines. In this case, ion 2 and magnesium 2. And the method is almost trivial. Just measure the redshift. And if Z1 is not equal to Z2, this tells you immediately that alpha must have changed from a redshift of Z up to today. What's the problem with all of this? The problem is that you're measuring wavelengths over here. And so you must be able to measure your wavelengths as accurately as possible. The error in your measurement of the wavelength is the most basic error in this. And so you must calibrate your wavelength scale. The way in which you measure your wavelengths must be accurate. And that, it turns out, is a huge problem as of today in optical astronomy. So let's take a look at this in more detail. What you're doing is that you're inferring changes in alpha and mu from differences in the measured line redshifts. And I should mention that, this idea is about 70 years old now. It comes from Davidoff in 1956, a long time ago. Almost, not very long after cosmologically distant galaxies were discovered. But there's a problem over here. You're talking about differences in the line redshifts, right? But now galaxies are not, simple objects. They're not point masses. They're gigantic objects with gas and stars, falling all over the place inside them. And gas clouds within galaxies, even inside the cloud, these have internal motions which are of the order of 5-10 kilometers per second. The gas is jiggling around the place. So now there's some gas moving towards you, some gas moving away from you, and that gives you the normal Doppler effect, not the cosmological effect, just the motion effect. And so the Doppler effect will contribute roughly approximately delta V by C of 10 to the minus 5 to the line redshift. So you'll have a cosmological redshift with the universe expanding, and then you'll have this jiggling of the gas inside the galaxy, which will give you about 10 to the minus 5 in the line redshift. To make matters worse, if I compare iron and magnesium as I did in the last slide, atoms from different species may be in different parts of the cloud, which means that they may have different velocities, which means that iron may be moving towards us, for example, magnesium may be moving away from us. Now, one of them has a positive velocity because it's moving away from us. One of them has a negative velocity because it's moving towards us. Now, when I compare the two, I will get a difference I'll get an offset in the observed redshift. But that's not coming from anything fundamental. It's coming simply because of motions in the cloud. I mean, who cares of motions in the cloud? And the problem is that, as I said, delta alpha by alpha is roughly delta z upon 1 plus z, approximately, with some constants in the front, which is approximately delta v by c. And so this seems to indicate that the best we can do is go down to about 1 part in 10 to the 5 for delta alpha by alpha, because you get delta v by c is about 10 to the minus 5 if delta v is about 510 kilometers per second. So that's pretty bad news, because it means that's like a hard limit on the accuracy we can get just coming from motions in these clouds. But astronomers can work around these things. And one easy way of working around it is to average over a lot of lines. So what you do is that you take a lot of clouds, a lot of galaxies, and in some galaxies, let's say magnesium and iron, magnesium is coming towards you, iron is going away from you. In another galaxy, iron is going towards you and magnesium is going away from you. Now I average these two measurements and the delta V will average out. But any cosmological evolution in the fundamental constants will not average out. And that's the game, basically. So then you average lots of lines, hundreds of lines, and then, with luck, the Doppler motions will average out, and you will be left with your signal that you're hoping to detect. That's one approach. The other approach, which is the one that I would always advocate, is to use what I would call special lines, where the line physics guarantees that the lines come from the same gas. And I'm not going to go into this in much detail, but I will just tell you there are such lines that you can use where the physics guarantees that the lines come from the same gas, and the Doppler motions don't matter. So about 20 years ago, Zuba et al. Came up with this nice technique based on averaging lots of spectral lines. And this is called the many multiplet method. And this is based on the idea that these wavelengths of these ultraviolet transitions in iron, magnesium, zinc, the same transition that we saw over here, magnesium and iron, these transitions have different dependencies in alpha because of relativistic corrections. And so, great, you measure lambda observed for different lines, you compare redshifts, and you determine delta alpha by alpha. And John Webb, Michael Murphy, and collaborators did this about 20 years ago, and they claimed changes in the value of alpha, that alpha was smaller at high redshifts. I'm not going to show you that plot because the result has gone away now. We discovered over the last 10 years that basically the problem is that there are systematic errors in the wavelength scales of optical spectrographs. And it looks likely that those errors gave rise to these apparent changes in alpha. And so therefore, that result is kind of not taken that seriously anymore. And that is a huge problem in optical astronomy. So that brings us to radio observations. So why is radio special? So, optical is beautiful because you have all these transitions, nice atomic transitions, many, many, many species. Radio is somewhat different because radio has molecules, it has access to molecules, and there are lots of molecules with very different transitions. In the optical, you tend to have simple transitions, which are electronic transitions. But in the radio, you have transitions of all kinds. You have inversion transitions, you have mixed transitions, you have fine structure, hyperfine structure, even the normal electronic. You have inversion transitions, all kinds of transitions. And some species, for example, OH, hydroxyl, has very interesting mixed transitions. Ammonia has mixed transitions. Methanol has mixed transitions. And what happens is that the line frequencies of these transitions are sensitive to changes in alpha and mu. So you might say, okay, who cares? It's just, it's complicating my life because now I have molecules with these different transitions. The molecules are more complicated than atoms. But the beauty of molecules is that I can use different lines from the same molecule. So I can have now, because my molecule is complicated, I can have one line which is coming from, for example, molecular rotation. I can have a second line coming from, for example, hyperfine structure. And these two lines have different dependencies on the constants. Now I can compare these two line frequencies. And because they're coming from the same molecule, it's the same molecule. So therefore, there's no relative motion. The lines are coming from the same gas exactly. In thermal equilibrium, all the lines should be at exactly the same redshift. So now, if I measure a difference in the redshifts, that's telling me the fundamental constants are changing. And so that's a beautiful method which basically overcomes the problems in the optical. The other reason that radio is wonderful is that we can do frequency calibration with errors that are the level of 1 meter per second. We can do velocity calibration with errors of 1 meter per second. And this is more than 100 times better than the optical. So it was pretty special in the radio, about 100 times better than the optical as of today. And so that means that wavelength calibration is not a problem in the radio, although it is a problem in the optical. The other thing that I will emphasize is that radio and optical, just like any techniques over here, will have their own systematic effects. We don't know systematics in the radio, but that doesn't mean that they don't exist. And it's important to have completely independent methods. So radio spectroscopy complements optical spectroscopy with very different systematic effects. So now, for example, suppose you're claiming evidence for a change in the constants. This is a huge claim, right? So you want to have, strong claims require strong evidence. And so you would like to have completely independent methods which give you the same result. And radio and optical allow that for high redshift galaxies. The sad thing about the radio, which is compared to the optical, in the optical, for example, we have more than 300, much more than 300 metal line absorbers known, thousands actually, but 300 at least with really good quality optical spectra. In the radio, we have only 6 redshifted radio molecular absorbers known, all at redshifts less than 0.9. In the optical, we go out to redshift of 6 roughly. But despite that, although there are so many more optical absorbers and so few radio ones, it turns out that the best techniques today remain these 2 techniques, which are based on hydroxyl lines, what are called conjugate satellite hydroxyl lines, and methanol lines. And these are special lines where the physics makes sure that the lines come from the same gas. And these lines have yielded today our best results for changes in alpha and mu, where delta mu by mu is less than 1 part in 10 to the 7. So if you like 10 to the minus 7 delta mu by mu, and delta alpha by alpha is less than 10 to the minus 6. So 1 part in a million in alpha and 1 part in 10 million in delta in mu. So we know today that we have no evidence as of now for changes in alpha and mu on timescales of between 3 to about 8 billion years from astronomical spectroscopy. And that is shown in this plot, these 2 plots over here, which summarize what I would call the state of the art today. That's a plot of delta alpha by alpha in units of 10 to the minus 6. So this number over here, for example, is 5 times 10 to the minus 6. This number is 1 times 10 to the minus 6. And that's a plot of delta mu by mu, again the same units, 10 to the minus 6. So this thing over here is about 2 times 10 to the minus 6. The scale is slightly different. And what is interesting is that the red vertical line, the dashed vertical line, basically indicates a divide between optical and radio. So these measurements are all optical. These measurements are all radio. These measurements are all radio. These measurements are all optical. And you can see that the error bars on the radio measurements, and I should mention these errors are all underestimated. The error bars, for example, over here are so small, you can't even see them. These come from ammonia and methanol measurements, and they are at about 1 part 10 to the minus 7, or 1 part 10 to the 7. And this is 1 part in about 10 to the 6. So you clearly have a much higher sensitivity using radio techniques, and you also have fewer systematic effects. But the downside is that, look at the fact that we can actually probe changes with the optical at much higher redshifts larger than 1. While in the radio, we are stuck with redshifts less than 1. So if alpha mu change at higher redshifts, these data will not let us constrain changes in alpha and mu. So we would love to push to higher redshifts with the radio, and we would love to improve the wavelength calibration in the optical. So these are 2 areas where people are really trying very hard to improve the situation. And that's one place where work is happening over the next decade. So that's where we're going. The first thing is that optical studies, as I said, are completely limited by wavelength calibration. And so we really desperately need new spectrographs, better spectrographs. And that's the work, that's one of the big pieces of work happening in the optical community. People are building spectrographs, for example, based on laser frequency combs on the next generation telescopes, 30-meter class telescopes, which will come up in about 5 to 10 years from now. By about 2030, we should have these 30-meter class telescopes, and that will let us do fantastic work at redshifts of 3 to 4, even 6, using these new spectrographs. And that should solve the problem we think of wavelength calibration. The next thing is theoretical work. And that's just the idea that you need to get new techniques. You need new spectral lines for these measurements. And so you need to do detailed theoretical calculations or numerical studies to determine the dependence of the line frequencies on the different constants. So for example, Janssen et al. Did that in 2011 for methanol, We did that for OH in 2003, 2004. This is the kind of work that needs to happen. And it's very detailed work for each individual molecule and each type of transition. The third thing you need to do is to carry out these lab measurements of the line rest frequencies. But you need to know the line rest frequency accurately so that you can put that thing into the equation. And you need to know what the isotopic structure of these molecules and atoms are. So lab measurements are an important part of such studies. And that's going on, for example, in the Joint Institute for Lab Astrophysics at Colorado. It's going on in the institute in Paris. And these are important measurements also. And of course, these also contribute to atomic clock studies directly. We're carrying out right now a new methanol study, and we expect that this will improve the sensitivity in delta mu by a factor of more than about 10. So we should get to 1 part in 10 to the 8 sensitivity in about a year from now, 6 months to a year from now. And that will be super interesting because, as I said, delta mu by mu is expected to change by a factor of about 100 compared to delta alpha by alpha. So pushing delta mu by mu is really the way to go for high redshift studies. The second thing which is happening in the radio is that, as I said, they're currently stuck because they have very few high redshift molecular absorbers. We just have 6 of them. And what's happening now is that we have a bunch of new radio telescopes or upgraded radio telescopes, like the Atacama Large Millimeter Submillimeter Array, the Jansky Very Large Array, and the GMRT, the upgraded GMRT. And that lets us, the first time, carry out these unbiased surveys, which are not biased by optical studies, unbiased completely, for radioatomic and molecular absorption. And this turns out to be really important because the earlier studies in the radio were all based on optical samples, and they were actually biased against molecular absorption for technical reasons. We won't go into that for now. But this is something now which opens up the field for in the next decade or so. And we have just, in the last year, Aditya Chaudhary, a really good student at NCRA, has just detected the 2 strongest known radio atomic absorbers at a redshift of 1.2 in exactly this kind of an unbiased GMRT 21 centimeter absorption survey. And this is the kind of work that we think will really happen over the next decade and which should change our radio view of the high redshift universe. So to summarize then, I hope I've convinced you that studies of fundamental constant evolution are really important for 2 reasons. One is that they test standard model of particle physics and relativity. But the second and less pragmatic reason is that they provide you a window on these unification theories, and more importantly, a low energy window on these theories where the low energy constants are expected to change with time. So you have the possibility of actually finding evidence for higher dimensional, high energy theories via fundamental constant evolution. Atomic clocks probe changes in alpha and mu on timescales of a few years. Currently, the best results of a 1 year timescales. And the best result is about 4 times 10 to the minus 17 per year on a 1 year timescale. And we hope that will improve over the next few years by about a factor of 10 to 100 once people put atomic clocks on the International Space Station. Astronomical studies complement atomic clocks by probing changes in the same quantities on billion-year timescales. And that's why they're special. They're completely different view of changes in alpha and mu. And the best current methods are conjugate satellite OH lines and methanol lines. Right now, we have 2 results. With the methanol lines at a redshift of 0.9, delta mu by mu is less than about 10 to the minus 7 over about 7.5 billion years. And with the conjugate satellite OH lines at a redshift of 0.25, delta alpha by alpha is less than 10 to the minus 6 over about 3 billion years. Those are the 2 best results that we have today for changes in the fundamental constants. So the punchline is that we don't have significant evidence today for changes in alpha or mu on giga-year timescale so far. We expect sensitivity improvements by a factor of about 10 in a year and by of the order of 100 by 2030. So I'll leave it there for now. Thank you.
Yeah, thank you, Nissim. Really wonderful, exhaustive talk.
Thanks, Kiran.
Yeah. There's a question. Please,
I'm sorry if
you
I
can
blew the
ask
show.
questions.
Yeah,
That's
students
fine in the
can
chat box.
students can put questions in chat box, or you can directly ask questions. Sir, I would
There is
like
one
to,
question.
yeah,
Yeah, go ahead.
sir, I just want to say something here. That
Yes,
was
yes.
a, yeah. That was a very good talk, sir. I was just thinking from which point I should start, and you have given such a nice idea of calculating things, alpha, mu, and how to correlate it with red shift and blue shift. Students will have, in fact, some ideas about it, and they will be highly inspired by this talk. And it is not very difficult. They can think on it and they can do it also. So thank you very much for a wonderful talk. Now I would like to ask students to put their questions in the chat box.
Thank you, Dr. Srivastava.
There is question by Advait Kulkarni. Why?
Yes.
What
Yeah.
is so special? What is so special about OH and CH3OH?
That's a good question. So there's nothing terribly special about them. I guess what is special about them is that what do you need to do this kind of a thing? What you need is molecules that you can detect in cosmologically distant galaxies, and you need molecules where there are multiple lines which you can detect, which have strong differences in the dependence on alpha and mu. And OH and methanol, hydroxyl and methanol, both fall in this category. So when we thought about OH about 20 years ago, the reason we thought about OH was that we had just used the GMRT. The GMRT had come online. I had just finished my PhD then. And Jairam Chengalur and I had just used the GMRT to basically look for, to detect OH in a bunch of these redshifted radiomolecular absorbers. And we realized that OH, the OH lines come from a mixture of lambda doubling and hyperfine splitting. So you have two physical mechanisms, lambda doubling and hyperfine splitting. And when you have two physical mechanisms, that means that there's a chance that the lines might have different dependencies on the constants. So then we sat down and we did second order perturbation theory and worked out the dependencies on the constants. And we found, oh my gosh, this is fantastic. They have very strong dependencies on alpha and mu. And we could use these lines to measure changes in alpha and mu. And that's why OH became special. And about 7 or 8 years later, Wim Ubachs and Paul Janssen did the same thing for methanol, where they found that methanol also has a lot of lines, even more than OH. And about 10 methanol lines have been detected now in one system at a redshift of 0.9. And we are using that now to chase after methanol, because the lines are much stronger than OH. And so that's why they're good. They're basically strong lines, and they have strong dependencies on alpha and mu.
Yes, thank you. But, Vijay, what are theoretical predictions? I mean, do theories predict some? I mean, do they give numbers on these
No.
changes?
No, unfortunately, no. That's the problem. That the standard models that you have are unification theories, and the problem is that we don't know which of those unification theories is correct. All of these theories have coupling parameters, and all of those coupling parameters can be tuned. And the problem is the same one, that basically the other predictions of those theories are at very high energies. So we don't know which theory is correct. So the hope is that we will actually be able to find changes in the constants, and that will tell us which of these theories is consistent with these changes. So we don't have a prediction from theories, unfortunately. We just have a general prediction the constants should change.
Okay. But thing is still open.
It's still open, yeah.
Gopi has asked some question. Gopi Vishwakarma has asked.
Yeah. So Gopi has asked, why do we need constants? And how can I say my calculations because if constants are right? Okay. So why do we need constants? Because in your theoretical models, you have parameters whose values you basically don't know. And so those are quantities which exist. For example, you might have a proportionality in your model, and now you put in some parameter in front of it. That parameter is a constant. Now, this begs the question, is that really a constant, or is it changing with time? So what do you do of its space? So what you do is that at the first level, you say, okay, it's a constant, and you test if your theories work out. You do experimental tests. And then maybe you say that, okay, fine, everything experimentally works out. So that is a constant. And you measure the value of the constant by experiment. The more general thing is that suppose that is not a constant, but is actually changing with space and time, then you must have an equation for that quantity. You will have a dynamical equation to determine the evolution of that quantity. And so if and so that kind of tells you that your theory is not complete. And yeah, for the second part, it's not so much a calculations. You have a theoretical model. Your model makes predictions, and you test those predictions, via experimental observations. And a theory is only as good as its predictions. And the reason, for example, we are so confident of general relativity is that relativity is the most tested theory around. Every test that relativity has been subjected to, it has passed. And so relativity is a powerful theory because it has been tested till the cows come home. The standard model also is been extremely well tested, but not as much as relativity, but extremely well tested. So that's how you can be confident that at least within some range of tests, that theory is a good theory. So Ashay Kadu has asked, do all the fundamental constants change with time or only alpha and mu? So the thing to think about is that in principle, all dimensionless quantities will change with time. Some of them may change more than others. So for example, as I said, mu is likely to change more than alpha. Delta mu by mu is likely to be more than delta alpha by alpha, at least in all the models that people have looked at so far. So the answer is that, yeah, you would expect generically that most fundamental constants, which are dimensionless, will change with time. Then Advait has asked, the measurement in atomic clocks is very small, of the order of 10 to the minus 17. How can you differentiate quantum errors and measurements? That's not a problem at all. I mean, quantum errors are not an issue at all over here. They're way, way, way smaller. The accuracy of the measurement is way above these quantum errors. Right now, in fact, we are limited by classical errors. They're or if you like, by general relativity errors, by the fact that the Earth is not an exact sphere, and so therefore the gravity is not exactly spherically symmetric, very close to the Earth. So that's a completely classical error.
So, sir, I have one more question.
Yeah.
Actually, I don't know much about it, but still I'm asking you that these constants, if they are changing with time, do they have any effect on the Big Bang, the time scale of Big Bang?
So, okay, so that's a very hard question to answer. The answer would be yes and no. I mean, yes, in the sense that, so basically, if the constants are changing, then certainly they would have a strong effect on the epoch of quantum gravity. So therefore, and that's the epoch just after the Big Bang. So the answer is yes, definitely. Can we observe this? That is much harder. And I would say the answer is probably no over there. But for example, in astronomy, two other things that we use to probe changes are what are called Big Bang nucleosynthesis, which happens a few minutes after the Big Bang. So basically, the amount of the light elements, helium, deuterium, lithium, and so on, the amount of those that we observe in the universe depends on the values of the constants 3 minutes after the Big Bang. Okay. So we can actually probe changes in the constants in alpha and mu a few minutes after the Big Bang. And we know that alpha and mu do not change by more than about 1 part in 1,000, 3 minutes after the Big Bang.
Okay. Thank you, sir.
So Vyom Kulkarni has, if fundamental constants do change with time, then will they change in places near black holes? The flow of time stops. Well, flow of time stops is not quite correct. There have been arguments, mostly by John Barrow and David Mota and collaborators, that you can actually have fundamental constant evolution in the regions, spatially dependent variation in the constants because of gravitational fields, and where you can have freeze out of the values of fundamental constants when an object forms. So that's spatial dependence. You can, in principle, have changes in the constants very close to black holes. You know, in the centers, for example, of black holes, where you have very strong quantum gravity effects. But there's no real claims of changes in the constants outside black holes so far. It would be very hard to probe these also.
So if there are no more questions, Kiran, can we ask Rani to, oh, still one question has.
So the Hubble constant actually, the Hubble constant changes with time. It's actually not a constant. The Hubble constant is actually the value of the Hubble parameter today. The Hubble constant has changes with time as the universe expands. Depends on the cosmological model, but basically it depends on if the universe is accelerating or deaccelerating or going at a constant speed. But basically, the Hubble constant changes with time, and you can actually work this out for a given cosmology. The Hubble parameter changes with time. That's the right way of phrasing it. The Hubble constant is today's value of the Hubble parameter, which is some 70 kilometers per second per megaparsec. That's not a fundamental constant, though.
Yeah, okay, maybe we can. There is one more.
Can we change all dimensionless constants with one single constant? That's actually a good question. In fact, there has been a debate. There's a paper about this about 15 or so years ago, where people were arguing in an ideal theory. Suppose you had a perfect theory of quantum gravity. How many constants must you have in such a theory? And so 3 fairly good theoretical physicists argued about this. And the 3 of them, one of them argued for 2 constants, 2-dimensionless constants. One of them argued for 1-dimensionless constant. One of them argued for 0. And so the answer is that we don't know. I think that's the best that we can do right now. And I think that's probably more kind of a philosophical question. I think that the thing that one will have to do is that you'd like to come up with a good theoretical model and reduce the number of constants to as small a number as possible. Even if you had one constant, that is telling you something about your lack of knowledge about the universe. So, so I would be wary about arguments for this, but there have been such arguments.
Okay, I think yeah, we can. I think that was. We can have vote of thanks.
Yeah, can I invite Ms. Rani Sheikh to give vote of thanks?
Yeah, hello, ma'am. I'm here.
Yes, Rani, go ahead.
A very good evening to all. It gives me an immense pleasure to deliver the vote of thanks to all the dignitaries assembled here. On behalf of Hindi Vritya Prachar Samiti's Ramniranjan Jhunjhunwala College, Department of Physics, for organizing a popular lecture on Do the Fundamental Constants Changes with Time? I would like to take this golden opportunity to thank our respected chief guest, Professor Nissim Kanekar. Sir, you honored this function with your inspirational thought. Your speech was so thought-provoking, it really made us think. Thank you so much for this wonderful speech. I extend my gratitude to our very own director, Dr. Usha Mukundan, our beloved principal, Dr. Himanshu Davda, our vice principal, Dr. Kiran Kulwankar. I would also like to thank our respected head, Department of Physics, Dr. Neeta Srivastava, my teacher colleagues, not only for spending time with us today, but also encouraging us to achieve many endeavors. Last but not the least, our beloved audience, that's my student friends, without whom this function would not be a success. Once again, I would like to thank one and all for your presence. Thank you so much.
Thank you.
Thank you. Fine. So we'll end the meeting. I will write to you, Nissim. Thank you, Nissim.
Sure. Yeah. Thanks, Kiran.
Thank you, sir. Thank you very much.
Yeah. You must, Devraj, you know Nissim? I don't know. Devraj, we have a colleague, Dr. Devraj Pawar. He works in Ayuka.
Yes.
He goes to Ayuka. Yeah.
I have a, at least the name is familiar, so I have a vague memory of having probably met him.
Okay. You might have met him.
Yeah.
Okay. Right.
Okay, thanks a lot, sir.
I know Nissim from his talks in NCRA and sometimes Ayuka, but he might not know me because
The name is definitely familiar. So yeah, it's possible. It's likely.
He's also Pune. He also did MSc from Pune.
Okay.
They were 2002, I think 2002.
Yeah,
We have
that
one more
increases the
colleague who
chances.
did,
Yeah.
and he had taken astrophysics that time. So. Okay. So let's
Thank you.
end the meeting.
Thank you,
We'll end
everyone.
the-
Yes.
Thank
Thanks
you.
a lot.